Here's the basic problem. If I just kind of sketch a cell, let's imagine we have our cell. Looks like this. It has a perimeter, and then we also have a active area on the cell. And we're looking at the cathode side at the moment. So we've got this cathode, which I'm just going to shade in. And that's the surface that we want to get air to, right? And then on the other side, we can't see because it's hidden behind the other side of the cell. That's where the fuel has to go. If you imagine a cross-flow situation just for the moment. So imagine we weren't feeding the air and the fuel from the same direction, but we're flowing air this way and flowing fuel that way. You can imagine how you might try to do that. And it comes down to what's called the interconnect, or there's a plate which we're putting in contact with this electrode to try to distribute current to it. And so the question is, what does that plate look like? So let me just move this down here for a second. I'm going to try to draw a plate that we might use to try to do this. Picture an object with certain thickness that has little notches cut in it. And what I'm going to try to do is design it in a way that this surface right here and there's this surface right here are going to form seals all along one edge of this plate like that. And then the other one is going to form a seal like that. And so the gas is going to approach from one side. Basically, air is going to come in this way. And because of those seals that are there, it can't squeak out the sides. So the air is going to be blowing through here, past the cell, and we're going to lead it along that path with these flow channels. The flow channels, their basic purpose is to allow enough volume for the air that we have to pass through to flow without too much pressure drop. The reason it isn't just all one big flow channel is we need to get current through it. And so that's the purpose of these additional features that are sticking out. And so we're making electrical contact everywhere along the electrode by virtue of these features that stick out. So that's what it looks like on one side of the interconnect. The other side, what we'll do is something like this, where we put notches going the other way. What we're doing here is we're now channeling the fuel going the other direction. The fuel is coming in this way. And of course, the whole point is we have another interconnect just like the one we just drew. It is, those flow channels are the ones that are making contact with the anode side, and that might have a seal too. So what you kind of end up with when you're all done, you stack this whole thing up and you're going to get a block of cells. Looks like this. And then because of the seals and the holes, you're going to end up like rows and rows of little holes, basically, that we're going to feed the air into. And it's going to go through, and it's only going to make contact with the cathodes. And then it'll blow out the other side through another set of holes into, the exhaust area. And then likewise on this side, we've got a bunch of holes interdigitated with the ones that I just drew. And those are the ones where the fuel's coming in. So they're passing each other crisscross and never mixing because of the seals that we're making against the cells. Once you're done, you built this whole thing and you have all these holes. It still doesn't solve the problem of how you get the gas into the holes. You now still have to keep the air and the fuel separate with some type of external manifold. And that's typically the way you would build this. Basically a ceramic block that's the same size as the stack. And it would have a hole in the bottom and you'd feed the fuel in, and then it would have seals all around the edges and then blow fuel into it. And then the fuel would then be distributed to all the holes and go out the other side. So this is called an external manifold. And of course, this never really worked because you're trying to make this material. It's a separate material. It has exactly the same expansion and contraction characteristics. The seals break, and then the air and the fuel start to mix up, and it just becomes very difficult. Workers started to figure out, well, okay, how do we fix this problem? And that's where the people started using internal manifolds. So let me describe how that works and how that sort of ends up solving the problem. So the basic idea is you don't want to have any type of separate attached gas distribution device. It's just impossible to manage. But you have a lot of ways of designing interconnect plates and cells in clever ways that allow you to get this gas distribution that's built into the stack as you assemble it, kind of like Lego pieces. So imagine we have a cell, and cells have a certain thickness to them. That thickness is usually not all electrolyte. Usually it's some type of support structure onto which you deposit all of the cell materials. You deposit the anode and the electrolyte in the cathode, only part of which has an active area. And I'm drawing an anode and a cathode. This is the cathode, and the other one is the anode. What we're going to do is the interconnects, we're going to design them in a way that they have sealing surfaces in different places. So on the fuel side, for example, which is the anode side, I'm going to build an interconnect plate that looks kind of like this. What we're looking at here is the cross section. And I'm totally exaggerating the vertical dimension to kind of so you can see what's going on. And we're going to put holes in it. And these are circular holes. So if you can imagine from the top, you're looking at this plate. What you have is a hole, and around that hole is a land, and it's surrounded by the rest of this plate. So it looks like a cylindrical feature that sticks up and it has a hole through it. That's what we're looking at, but on cross section. And then we're going to put a hole in the cell itself, like that. Same thing over here. So we're looking at in cell and cross section as well. And then I'm going to repeat this. I'm going to place it right there on this previous cell. And then I'm going to put seals in. I'm going to pick orange for the seal. So our seal is here. And it's also here at the edges of that cell. And repeating down here, there's another seal here. And then wherever these lands stick up from the interconnect, I'm going to put a seal there as well. And so now what we've done is we've created a contiguous sealed space, which only will ever see fuel gas. So we've got our fuel, and we're actually going to feed it into the bottom. So somewhere at the bottom of all this is a bottom cell. And this fuel is going to flow up through this extended hole that goes all the way through the stack. And at each point, it is going to split off and go to the anode of each cell. So some of it will go like here, and the rest of it will go through. And some of it will go here, and the rest of it will go through, and so forth. So the gas goes up through this chimney, and then whenever it penetrates through into the anode compartment of one of the cells, then it can turn that corner and then start flowing across the anode. And then at the other side, we can collect. So gases are flowing down this way. Gas is flowing, the exhaust comes in through here, and then we're flowing down these holes. Exhaust joins from here and then goes down these holes. So as we accumulate gases going down the flow channels. So this is our exhaust. And the way the topography of this, the way we've arranged the seals, there's no mixing with the air. So the air comes in here. And it's got this little chimney sticking up. It's sealed around the hole, and so the air just goes around it and make contact with the cathodes. It just goes around this chimney and goes through and around and through. This is what you call semi-internal manifold, where we've internally manifolded the fuel, but we still have to externally manifold the air. That's less challenging because you can always just stick the whole stack into some type of window, and then you put air pressure across it and the air will blow through the stack because we have these openings that allow the air through. Air can just kind of be passively externally manifolded. There are more complicated designs, and I'll show you kind of an example of this, where you do some internal manifolding of the air as well. So you can create another set of analogous oppositely directioned lands and seals that stick the other way and allow you to collect the air on one side of the cell and then port it up through some type of chimney. In the language of the SOFC, this is called the interconnect, this object that has all these features built into it. Interconnect or interconnect plate. In the PEM literature, it's called the bipolar plate or flow field plate, but it's basically the same thing. There's some fluid mechanics issues that impact the design of these plates. Like how do you exactly design the features into these plates to allow gases to flow through in the appropriate ways for either an SOFC or a polymer electrolyte fuel cell? There are some differences. So what I wanted to do is show you some actual patent drawings, which I think help kind of illustrate this. And this one is from Cirrus Power. So this is an example of what's called a semi-internally manifolded stack. An inlet and an outlet of the fuel are manifolded, and the outlet of the air is manifolded, but the inlet of the air is not. And the idea there is, well, you don't have to control the inlet air. If you just reduce the pressure across the cell, it's just going to suck air in naturally. One of the things Cirrus Power sort of pioneered was the use of stainless steel to make these things as inexpensively as possible out of stamped metal parts. They stamp out a sheet of stainless steel. They put holes in it to allow the gases to get in and out of the cell. And then onto that plate, they will deposit like it's a porous metal anode support, and then they put on an anode. Then they cast on top of the anode, they cast the electrolyte. On top of the electrolyte, they cast the cathode. The thickness of that cell is just tiny. The actual thickness of the electrolyte, I think, is like 4 microns. It's very, very thin. Of course, that's good because we want to limit the ohmic resistance. What's great about things that are thin is they're actually flexible. And even though it's made of ceramics are super brittle, but you could just take it and just flex it like that. It's like flexing a piece of thin aluminum or something, and that's because it's so thin that you can actually handle the radius of curvature. It doesn't cause too much stress. That's one of the things that's beneficial about these really thin films. You're not so cautious in the manufacturing process about not putting any forces on them. And then that gives you this flexibility. You can lay them on top of other metal objects and weld them, and that's kind of what they do. So imagine this cell, it's this thin sheet. It's cut out in roughly the same shape as the interconnect plate, which I have showing. And what we're looking at is the two sides of this cell. This figure is the air side. So what we're looking at is the interconnect plate on the cathode side where the air is going to flow. The cell is sitting on top of this, comes down, and the cathode makes contact to this plate. And so the air side, if I draw it in, this is the air over here. There are these features, and what the drawing is showing are features in the metal that stick up from the plane of the metal surface. And there are two main ones. This one right here is sticking up right along here. That makes contact with one side of the cell. And then there's another one over here that makes contact with the other side of the cell. And there's also a gasket that sticks up, and that's what this is right here. This gasket sticks up as well. So I'm drawing in what sticks up from the plate. There's another one over here that sticks up. Oh, this is sticking up. And so all those surfaces are sticking up above the plate, and the cells rests on that. And the air comes in this way. The air comes in this way through the space that's left between the lands and the bottom of the plate. So right in here, there's an opening. There's another opening over here. Air can come in. And then it hits a pin field. So what this is, these are little features in the interconnect that have been stamped in that push the metal up. And if I show another figure, what that looks like this. So basically there's these little features in the metal that are bent up and stick out the same distance as the other vertical features that are sitting on the plate. And they are what make contact to the cell. So along each of these pinpoints, and just drawing a few of them, that's where all the current flows. So the current doesn't literally go through as a uniform current density. It does through the cell approximately, but then at each pinpoint, You're collecting a little bit of current, sucking it into a pin, goes up into the interconnect, goes to a pin on the other side, and then gets redistributed on the anode. So the air actually flows through this pin field. And one of the other purposes of having a pin field like this is that it creates some, like, it's like a porous media that the air has to flow through. So as the air flows through the pins, there's a little bit of pressure drop, creates a little bit of resistance, and it kind of makes the flow of the air more uniform than it would be if you didn't have any of those features present. Sort of like, if you make espresso, you pack all the coffee in and drive the water through it as a packed bed that has pressure drop, that forces the water through at a fairly uniform rate wherever you are in the filter bed of your espresso. The air flows through amongst all these pins, and then at the end, it gets sucked into the air channel. And that's where this is our first manifold. So here's the air manifold, air outlet manifold, which then allows the air to flow up or down the stack. You'll notice the two gaskets that we have that I drew in as sticking up, they are surrounding the fuel manifold, which is sealed from it on this side. So we've sealed off around the fuel manifolds. The airflow is much bigger than the fuel flow, as we've been talking about. So the air outlet manifold is enormous compared to the fuel manifolds, which are very small because they are not carrying nearly as much gas. That's the air side. Okay, so here's the fuel side. The way this particular cell is manufactured, the seal on the anode side is actually a weld. So they take the cell, which is made of stainless steel. The stainless steel part is on the anode side, and the whole cell sits on top of the stainless steel. So to make a seal, they just take the uncoated side of the stainless steel, which has all the holes in it, and they literally weld it to the interconnect plate. That's what this line is. So this line is the weld. And that seals off the air, creates a continuous fuel compartment. And so the fuel comes in here. So there's the fuel inlet manifold. That, like the other side, goes through a pin field. So the gas, the fuel spreads out, goes through this pin field, it gets ported around this way, and then out through these other holes. And so this over here, these are the exhaust manifold. If you actually look at the left side of the cell as I've drawn it, fuel is coming in the middle because it's coming up this fuel port, and it's being distributed left and right on the anode side. The air is coming in to the right and left of it, so they crisscross. There's a little bit of cross flow going on, but it's minimal. Again, that's helped a lot by the pins. Pins help ensure that most of the pressure drop is across this pin field. We're at low gas density, fairly low flow rates, and you end up with mostly laminar profiles. Laminar flow has a lot of resistance, so that actually it can be a good thing because it means that the gas flow distribution ends up being much more uniform than it would be if you were dealing with turbulent flow. So when the whole thing is done, you end up with a series of cells. They're all stacked up. The little gaskets complete and seal up the manifold along the entire height of the stack. And then to keep pressure on it, to make sure electrical contact is uniform and maintained all the time, even though there's a little bit of expansion and contraction, the way they do that is with tie bolts. So they run bolts all the way up and down the stack, and then put on spring-loaded nuts on the top, brings it down and holds it in place. And so that explains sort of the last features on this plate. So these other holes, those are all bolt holes. They don't carry any gases. Those are just holes for threaded tie rods that run all the way through the stack. Anyway, that was the introduction to internal manifolding. Everything you see is going to be some kind of variations on this, different ways of sealing, prevent the fuel and air from mixing in different ways. But it all comes down to this basic idea